Today we're taking a look at continuous compound interest. Now, you'll remember from a few units ago, we actually learned the formula for the general compound interest. And it went like this. The amount you earn is equal to the principal, that's the amount you start off with, times your growth ratio, which is 1 plus your percentage rate at which your money is growing, or your interest rate I should say, divided by n. That's the number of times your interest is compounded in one cycle. So if it was compounded quarterly, that n is 4. If it was compounded monthly, the n was 12, so on and so forth. Now, this was all raised to the power of n times t, where t is the number of years that money was left in the bank. Now, that was the general compound interest formula. Today we're going to talk about this idea of continuous compound, which is the fact of compounding interest every second of every hour of every day of the year. Now, that sounds like a lot of money, but it actually just works out to this nifty little formula that goes like this. A, the amount you have, is equal to P, the principal that you start off with, times E, this number E, which we'll get to here in just a minute, all raised to the interest rate as a decimal times t, the number of years that money is left in the account. So this is known as the PERT formula here because it spells out PERT really nice. Not like the shampoo, but PERT like the continuous compound interest formula. So let's get on to today's notes here. The next section of your notes actually call for you to do this activity. So take a minute and either on your graphing calculator or in Desmos, it's really actually a lot easier in Desmos, graph the function f of x equals 1, so $1, that's going to earn a 100% interest rate, and that's given here by this number 1 here, divided by x, all raised to the x powered. So essentially what we're doing is we're taking $1, we're investing it for 1 year, and we are going to compound it at different rates, or sorry, different number of times, okay? So when x is equal to 1, that represents compounding that interest one time in that year. And you see that we get back $2. We've doubled the money, which is what you would expect from a 100% interest rate. Now, let's move to semi-annually. If we compound that interest semi-annually, you'll see that the money we have here is actually just $2.25. So we've earned actually an extra quarter. Not bad. How about if we compound it quarterly? Now our final amount is $2.44. All right, let's move up to monthly now. That's going to give us a total value of $2.61. And how about if we go all the way up to 365? Remember, if 365 is the value of x here, that means we are compounding this daily. So 365 is going to give us this 2.71, so $2.71 is what we'll have in the bank. Well, you can see here as we increase those values, next up to 1,000, and then finally up to 8,760, which is actually the number of hours in a year. It's a lot of hours. Then you can see that we're actually not getting much bigger than 2.71. So what's happening here is that you see this graph of this line, and it's actually converging on this limit. And this limit is this number 2.71812 ... and that number is known as E. So right down there at the bottom of your notes there, it says there's a limit on the amount that can be earned, and that amount earned is this amount E, 2.7182, yada, yada, yada. All right, so let's move into a few examples here after our activity. And we see that Mana invests $8,218.16 in a zero coupon bond paying 4.5% compounded semi-annually. After 25 years, the value of the bond will be about $25,000. Not bad, Mana. How much would Mana's investment have been worth after 25 years if it were compounded continuously? So they're calling on us to use the PERT formula here, and we're just going to write it out here again so we remember what it all stands for. P is our principal amount. Here's the amount that Mana invested, so $8,218.16. E is just a number that we're going to find on our calculator here, and we're going to raise that to the rate here. Now our rate is just going to be converted to a decimal, so this is 0.045 and times t, the number of years, which is 25. All right, so let's go over to our graphing calculators. And on our graphing calculators, we're going to enter in that exact formula here. So we're just going to type in $8,218.16. Now the E button here can be found right up and down here in the lower left-hand corner on your graphing calculator. It's right above the ln. So we're going to hit second function, ln, and you see that it raises E, and it raises it to the power, and we'll enter in our interest rate, 0.045. And then we're going to multiply that by the number of years that was in there at 25. Close our parentheses, and when we press enter, we see that our final amount here is $25,313.71. So our amount, A, here, is going to be equal to $25,313.71. So you can see here, she made $25,000 investing it in a zero coupon bond that was calculated semi-annually, twice a year. Whereas if she would have invested it in a continuous compound, she would have earned $25,313. So she would have earned an additional $313.71. All right, let's check out example 2. It says $850 invested in an annual interest rate of 6%. Compounded continuously. What is the amount of the account after 10 years? So simple little plug and chug of our PERT formula here. We got E raised to the 0.06%, and we're going to multiply this by 10. When we do that in our calculators, we get that out to be $548. $548.80. So you can check my work. You should be getting some practice punching that into your calculator yourself. But go ahead and make sure I got the right numbers. All right, example 3 says an amount L of a certain radioactive substance remains after T years is given by this formula here. L equals B times E raised to the negative 0.0001 T, where B is the initial amount of the radioactive substance. It says if 2,000 grams are left after 6,000 years, how many grams were present initially? So here we are looking for our value of B. All right, the L value we know is 2,000. So there's 2,000 grams left. The initial amount B is what we want to look for here, what we want to find. And we're going to raise that E to the negative 0.0001 times T, which is, in this case, 6,000 years. All right, so this is actually just a number. And again, we can get that number by punching that into our calculator. And that number is attached to B by multiplication. So what I'm going to do is I'm just going to divide both sides by that number to get B by itself. All right, so I'm going to do that over there, and now this side will go away, and B will be equal to 2,000 divided by E to the negative 0.0001 times 6,000. So go ahead and take a second to punch that in your calculator. When I do that, I'm going to get 3,644. So this is the initial amount that we started with 6,000 years ago. All right, finally, example 4 says a machine used in an industry depreciates, remember that means decays, so that the value T years is given by this equation here. If after 3 years the machine is worth $12,000, what was its original value? So this is the initial amount. This is N sub 0. That's what we're looking for here. So let's substitute in the values we know. We know 12,000 is what it's currently worth. N sub O is what we're looking for. E, again, remember, it's just like a number, an irrational number like pi. E to the negative 0.25 times T, which is 3 years. All right, again, keep in mind that this is just a number. I can multiply that out into my calculator, which means it's attached by multiplication here. So if I divide both sides of my equation by that, negative 0.25 times 3, then I will get my initial value, or what it was worth when it was first purchased. All right, so I'm going to check that on my calculators. You check that on yours. And I get N sub 0 is equal to $25,404 approximately. So that was its original value. And that's a little bit about using this letter E, or this number E, I should say. Keep in mind that E is equal to 2.718281.